February 16, 1943, the screwdriver quivered slightly in senior engineer Klaus Hermann's hand as he unsealed the metal casing of the captured American radio unit. Around him, 5 of Germany's most skilled radio specialists leaned in, eager to inspect the device that had fallen into their possession during the recent clash at Kasserine Pass. For 3 years, they had heard constant assurances from Berlin that American technology was inferior, mass-produced junk created by a nation of shopkeepers and factory laborers. The Wehrmacht's Radio Intelligence Division had repeatedly reported that U.S. forces relied on obsolete equipment, crude designs, and poorly trained operators. Yet, something didn't add up. Allied troops maintained seamless communication across staggering distances. Their fleets never lost contact. Their ground units coordinated with a precision that hinted at something far more advanced than the crude radios German propaganda described. The casing opened to reveal an SCR-508 radio set, captured intact from an American M4 Sherman tank destroyed in the Tunisian highlands. What Hermann and his team uncovered in the next 72 hours would demolish every assumption German planners held about American industrial capacity, technical expertise, and the future course of the war. The mathematics of radio engineering were about to expose a truth more devastating than any defeat on the battlefield. The systematic analysis of American equipment revealed not merely a technological disparity, but an industrial gulf so immense that Germany's downfall was already encoded in its frequency crystals, automatic circuits, and production methods the Reich could never hope to replicate. The story began on February 14, 1943, in the Kasserine Pass. General Erwin Rommel's forces, in a desperate counterattack against inexperienced American troops, had won a tactical victory, driving the U.S. II Corps back 50 miles and destroying over 100 tanks. Amid the wreckage, German technical intelligence units moved swiftly, scavenging for weapons, papers, and devices that might unveil Allied capabilities. Hauptmann Friedrich Weber, commander of a signals intelligence detachment attached to the 21st Panzer Division, had standing orders to seize any American radio gear intact. In a crater east of the pass, his team discovered an abandoned Sherman tank, its turret blasted off by an 88mm shell, but its radio compartment miraculously untouched. Inside, Weber found not one but 2 complete radio systems, the SCR-508, used for tank-to-tank communication, and an SCR-510 receiver. Both were fully intact, with their crystals, cables, and even technical manuals still strapped in their brackets. Weber immediately ordered the radios transported to the nearest German testing site, aware that the find could yield invaluable intelligence on American communication methods. The sets arrived at Technical Evaluation Station 12 on February the 16th. Hidden in an underground complex beneath Tunis, the facility housed Germany's leading radio engineers, men responsible for designing the Wehrmacht's own communication gear. Senior engineer Klaus Hermann, former chief designer at Telefunken, led the analysis team. With him were experts in frequency generation, circuit design, production processes, and signal interception. They began with an external inspection. The American radios were encased in heavy-gauge steel, painted olive drab, with rubber seals protecting every joint and connector. Hermann noted in his initial report that the build quality exceeded anything he had seen in German equipment. The cases were engineered to withstand water, dust, shock, and extreme temperatures, conditions that would cripple most German radios. But when they opened the units, the first true shock came. Inside, everything was standardized, modular, and clearly built for mass production. Every part matched the specifications in the accompanying manuals. There were no hand-tuned adjustments, no technician markings, no small inconsistencies demanding expert assembly. This was machinery designed to be built by the millions, by semi-skilled workers in factories that could be duplicated across a continent. Lieutenant Hans Schreiber, A frequency control specialist examined the crystal units that determined the radio's operational channels. He had expected simple, low-quality crystals, perhaps even repurposed civilian parts. Instead, he discovered precision-cut quartz oscillators, each ground to tolerances measured in parts per million, and hermetically sealed in metal holders. The SCR-508 contained 10 crystal-controlled channels, each individually packaged, interchangeable, and marked with exact frequency values. Schreiber checked the count twice, unable to believe his eyes. In Germany, crystal-stabilized radios were reserved for high command and aircraft, where their cost and scarcity could be justified. Yet here, in a standard American tank radio, 10 precision crystals were installed as casually as light bulbs. He removed one for closer inspection. The quartz was flawless, the electrodes perfectly aligned, the frequency marked with exact precision. A single crystal of this quality would cost more than an entire German Fuji 5 radio in materials and labor. And yet the Americans were fitting 10 of them in every tank, producing thousands of such sets. The team's testing revealed even more unsettling discoveries. The radio operated using frequency modulation, FM, instead of the amplitude modulation, AM, used by German forces. FM provided static-free communication and strong resistance to jamming, but required more complex circuits and extreme manufacturing accuracy. German engineers had once considered FM for military use, but rejected it as impractical and too expensive for wartime production. Yet, here it was, an FM radio mass-produced and installed in every American tank. The circuitry featured automatic frequency control, AFC, that kept the signal stable without manual tuning. German sets required constant operator adjustment to counter temperature drift, component wear, and voltage fluctuation. American radios, it appeared, tuned themselves. Senior engineer Hermann began drafting his first report to Wehrmacht High Command. Each sentence challenged years of propaganda and intelligence assumptions. He concluded that the captured American radio demonstrated a level of industrial sophistication far beyond Germany's reach. Its components were crafted with precision that demanded specialized factories, trained technicians, and rigorous quality control, none of which existed in the Reich. More alarming still, the radio was clearly not a prototype or special-issue device. Every detail of its design indicated mass production. The Americans were manufacturing these by the thousands. Over the next 3 days, Hermann's team tested every function of the captured radios. They connected them to power sources, antennas, and diagnostic instruments that filled the subterranean lab. With each test, their unease deepened. The SCR-508's transmitter produced 25 watts of clean FM signal on any of 10 selectable channels. The switching mechanism was elegant, dependable, and required no technical expertise to use. A tank commander simply rotated a knob to select a preset crystal, and the radio automatically switched frequencies, retuned its circuits, and maintained perfect transmission quality. In German radios, changing frequencies required a trained operator to manually adjust multiple controls, replace coils, and spend several minutes retuning the equipment. Range tests proved even more disturbing. Using a captured American whip antenna, the team established contact with a monitoring station 20 km away. The FM signal came through clearly without the static, fading, and interference that plagued German AM communications. Even when they deliberately introduced electrical noise from a tank engine, the FM receiver's limiter circuits stripped away the interference, delivering clean audio that German operators could only dream about. Lieutenant Schreiber focused Heiss's examination on the crystal oscillator circuits. He traced every component, measured every voltage, and documented the design in meticulous detail. What he found confirmed his worst fears. The crystal control system was not just sophisticated. It was impossible to duplicate with German manufacturing capabilities. Each crystal oscillator required a precisely cut quartz plate ground to specific dimensions measured in thousandth of a millimeter. The crystals were then mounted in evacuated or gas-fill holders with electrode spacing controlled to tolerances that German factories could not achieve in mass production. Temperature compensation circuits maintained frequency stability across operating temperatures from -40 to +60 degrees C. Schreiber calculated that producing one crystal to American specifications would require approximately 40 hours of skilled technician time in German laboratories. The Americans had installed 10 such crystals in a single tank radio. With thousands of Sherman tanks already produced and similar radios in American Jeeps, trucks, and command vehicles, the Americans were producing millions of precision crystals annually. He asked the obvious question in his report. Where were the Americans getting enough trained technicians to produce millions of precision radio crystals? The answer, when it came from intelligent sources, was even more disturbing. The Americans are not using highly trained technicians. They had industrialized the entire process. New factories in cities with names like Chicago, Newark, and Fort Wayne employed thousands of semi-skilled workers, mostly women, operating specialized grinding machines that produced crystals automatically. Precision measurements were performed by optical comparators and frequency counters, not skilled technicians. Quality control was statistical with random samples tested rather than individual inspection. The Americans had transformed a laboratory art into an industrial process. The examination of the radio's receiver section revealed even more advanced technology. The superheterodyne circuit design was similar to German receivers, but the components were superior in every measurable way. Vacuum tubes were manufactured to tighter tolerances with characteristics precisely matched to circuit requirements. Capacitors and resistors had stability ratings that German components could not achieve. The entire receiver was designed for alignment by semi-skilled technicians using simple test equipment rather than requiring radio engineers with years of training. Most disturbing was the modular construction. Every major subsystem, transmitter, receiver, power supply, and control unit was a separate replaceable module. A tank crew could remove a failed unit and install a replacement in minutes without tools or technical knowledge. Damaged modules would be returned to depot facilities for repair or disposal. This approach required massive industrial capacity to produce spare modules, but it meant that American tanks maintained communications capability under conditions that would leave German vehicles radio silent for days, while technicians performed field repairs. The team examined the technical manuals that accompanied the radios. These documents, printed on high-quality paper with clear diagrams and simple instructions, assumed that operators had minimal technical training. Operating procedures were reduced to numbered steps. Troubleshooting guides used decision trees that any soldier could follow. Maintenance instructions specified exact replacement intervals for components rather than relying on operator judgment. Herman realized that these manuals revealed as much about American industrial philosophy as the radios themselves. The Americans had accepted that frontline soldiers were not technicians. Rather than train every radio operator to understand electronics, they had designed equipment that any reasonably intelligent soldier could operate and maintain using simple procedures. This required more sophisticated equipment, but it solved the fundamental military problem of maintaining communications under combat conditions. German radios, in contrast, required skilled operators who understood radio theory, could perform field repairs, and possessed the technical judgment to keep temperamental equipment functioning. These operators required months of training and years of experience. They were irreplaceable assets, and when they were killed or wounded, their equipment often became useless to whoever inherited it. By the end of the third day, the examination team had documented every circuit, measured every component, and tested every function of the captured American radios. Their report to Wehrmacht High Command was over 200 pages of technical analysis, supported by photographs, circuit diagrams, and component specifications. The conclusions were devastating. The Americans possessed radio technology that was 5 to 10 years ahead of German equipment in key areas. Frequency modulation, crystal control, automatic frequency circuits, and modular construction represented fundamental advantages that could not be overcome by superior tactics or operator skill. More critically, American radio equipment was designed from the start for mass production. Every aspect of the design reflected an industrial philosophy that Germany simply did not possess. Hermann's report estimated that Germany would need to build 30 new specialized factories, train 50,000 additional workers, and invest resources equivalent to the entire annual Luftwaffe budget to match American radio production capabilities. Even then, Germany lacked the raw materials, particularly high-quality quartz crystals, and certain rare elements needed for precision components. The conclusion was inescapable. American industrial capacity had made technological superiority militarily decisive. The report reached Berlin on February 25, 1943. It was classified most secret and distributed to only a handful of senior officers in Wehrmacht High Command and the Reich Ministry of Armaments. The response was silence. No new factories were authorized. No crash programs were initiated. The implications were too devastating to acknowledge. But technical testing Station 12's work was only beginning. Over the following months, more American equipment fell into German hands. Each capture provided new evidence of American technical and industrial superiority. An SCR-300 radio, the famous backpack walkie-talkie, revealed FM technology, miniaturized into a portable unit that weighed only 18 lb, yet provided reliable communications up to 5 kilometers. German portable radios of comparable range weighed over 40 pounds and required external battery packs that added another 20 pounds. An SCR-299 captured in Sicily in July 1943 stunned the examination team. This was a mobile long-range communication station installed in a truck with an integrated power generator. The transmitter produced 350 kW of power across a frequency range from 2 to 18 MHz with crystal-controlled stability and the ability to change frequencies in minutes rather than hours. The SCR-299's associated receiver was a helichromine design with 15 vacuum tubes, multiple conversion stages, and a crystal filter for improved selectivity. German long-range communications equipment of similar capability existed, but only in fixed installations requiring building-sized antenna systems and dedicated power plants. The Americans had packaged equivalent capability in a vehicle that could be driven anywhere and set up in an hour. Each examination revealed the same pattern. American equipment was designed for operation by minimally trained users, mass production by semi-skilled workers, and maintenance by following simple procedures. German equipment required skilled operators, hand assembly by trained technicians, and field repairs by electronics experts. One philosophy scaled to millions of units and global deployment. The other did not. The technical intelligence reports flowing from Tunisia, Sicily, and later Italy documented not just individual radio sets, but an entire communications philosophy. American forces maintained constant contact from squad level to theater command through multiple layers of radio networks. Platoons had SCR-536 handy-talkies. Companies had SCR-300 backpack radios. Battalions had vehicle-mounted SCR-508 and 600T SA-8 sets. Regiments had SCR-193 and 299 long-range equipment. Each level could communicate with the levels above and below, creating a web of connectivity that German forces could not match. More critically, all American radios used compatible frequency systems and interoperable equipment. A forward observer with an SCR-300 could contact an artillery battalion 20 kilometers away using an SCR-608 because both used FM on compatible frequencies with crystal-controlled stability. German forces, in contrast, operated multiple incompatible radio systems, each requiring different frequencies. different modulation types, and different operating procedures. By summer 1943, German signals intelligence had documented over 50 different American military radio types, from handheld transceivers to airborne command sets. Production estimates derived from captured serial numbers and intelligence reports suggested that American factories were producing over 100,000 military radio sets monthly. German production, including all services and types, reached approximately 15,000 units monthly at peak capacity. The examination teams began analyzing captured American manufacturing documentation. Technical orders, parts lists, and maintenance manuals revealed the infrastructure behind American equipment. Components were standardized across multiple radio types. Vacuum tubes used common base configurations. Crystals followed standard holder designs. Even screws, nuts, and bolts followed unified thread standards that allowed interchangeability. This standardization meant that American factories could shift production between different radio types without retooling. A plant producing SCR 508 transmitters could switch to SCR 608 units by changing only a few fixtures and component types. Parts from one radio type could often be salvaged to repair others. The entire system was designed for flexibility and scale. German manufacturing, in contrast, used custom components for each equipment type. The FUG-5 tank radio shared almost no parts with the FUG-10 aircraft radio. Despite similar electrical functions, each type required dedicated production lines, unique test equipment, and specialized spare parts inventory. Changing production priorities required months of retooling and retraining. Oberg engineer. Hermann transferred to a larger technical intelligence facility in northern Italy by autumn 1943. It spent increasing time analyzing American manufacturing methods rather than just equipment design. His reports to Berlin evolved from technical assessments of radio circuits to strategic warnings about industrial capacity. He documented the American electronics industry's explosive growth. Companies with names like Galvin Manufacturing, later called Motorola, had transformed from small radio manufacturers into massive military contractors. Helicopters, a maker of amateur radio equipment, was producing sophisticated military receivers in quantities that exceeded total German radio production. Western Electric, the manufacturing arm of the Bell telephone system, operated factories employing tens of thousands of workers, producing crystals, vacuum tubes, and complete radio sets. These companies had not existed as major military suppliers before 1941. The Americans had created an entire military electronics industry in less than 2 years by converting civilian factories, training new workers, and applying mass production techniques refined in automobile and consumer appliance manufacturing. Detroit's automotive engineers had designed radio production lines that operated with the efficiency of car assembly plants. The German radio industry, centered in Berlin, Munich, and Hamburg, remained organized as it had been in the 1920s. Small manufacturers produced specialized equipment using skilled craftsmen. Production quantities were measured in hundreds per month, not thousands per week. Quality was maintained through individual inspection and hand adjustment, not statistical process control. Automated testing. Hermann's December 1943 report to the Reich Ministry of Armaments was titled The American Radio Industry, an assessment of industrial capacity and strategic implications. It documented American electronics production in devastating detail. United States industry was producing annually what would take Germany 20 years to manufacture. The gap was not just technological, it was industrial, organizational, and philosophical. The report concluded that American factories could manufacture enough military radios to outfit 1,000 divisions, even though the United States fielded only about 90. This excess capacity meant that American forces possessed virtually limitless replacement equipment. Damaged radios were not repaired on the front lines. They were swapped out. Obsolete models were withdrawn and reassigned to training commands. New, improved designs were continually introduced, not as experimental prototypes, but as mass-produced equipment distributed across entire combat zones. German forces, by contrast, conserved every radio with extreme care. Field technicians carried out repairs under battle conditions, scavenging parts from destroyed units to keep others functional. Replacement sets arrived sporadically, if at all. New models remained in small-scale production because retooling would slow output of existing types. The Wehrmacht operated radio sets designed in the early 1930s alongside more modern versions, creating maintenance headaches and complicating training. The situation regarding crystal supplies was especially dire. By late 1943, German quartermasters estimated a need for roughly 5 million precision crystals for current radios and planned upgrades. Domestic output amounted to only about 200,000 per year. Even with massive investment, it would take over a decade to meet demand. The Americans, according to intelligence assessments, were producing some 30 million crystals annually. They had solved the quartz shortage by securing deposits in Brazil, opening mines in Arkansas, and experimenting with synthetic crystal growth. American crystals were not only plentiful but superior, achieving frequency stability levels that German laboratories could scarcely measure, much less reproduce. Examination of captured American testing instruments revealed yet another layer of industrial disparity. U.S. radio factories employed automated test units that measured frequency, output power, modulation quality, and sensitivity within seconds. These test devices, highly advanced instruments themselves, were produced in such numbers that every assembly line workstation had its own dedicated set. German factories, on the other hand, relied on manual testing that demanded skilled technicians and several minutes per unit. One captured device, a Measurements Corporation signal generator, became a prized possession at the German testing facility. This single unit, considered routine equipment in American plants, could generate precisely calibrated signals across the full radio frequency spectrum. It cost about $300 to produce. The equivalent German setup required an entire laboratory of separate oscillators, attenuators, and frequency meters costing thousands of Reichsmarks and constant recalibration. By early 1944, the verdict from technical intelligence was unmistakable and alarming. American communications superiority was total, irreversible, and accelerating. Each month, American factories turned out more radios than Germany possessed in its entire armed forces. Every captured specimen revealed incremental enhancements, refined engineering, and manufacturing precision that Germany could not rival. The introduction of American radar systems in late 1943 and early 1944 confirmed this reality with even greater impact. Radar represented radio technology taken to its ultimate limits. Microwave frequencies, pulse methods, and complex signal processing. The Americans were mass-producing radar for ships, aircraft, and ground stations with the same industrial efficiency applied to standard radios. A captured SCR-584 fire control radar examined in March 1944 demonstrated capabilities that German scientists had only imagined. Operating at the extremely high frequency of 3,000 MHz, it used a precision tracking mount with automatic following circuits and achieved accuracy, allowing anti-aircraft guns to destroy targets with lethal precision. The SCR-584 weighed over 10,000 pounds and required a dedicated vehicle, yet American factories were producing them in the hundreds. German radar research had centered on long-wave systems under 1,000 MHz, since German industry could not produce the specialized vacuum tubes necessary for higher frequencies. The magnetron tubes used in American microwave radar demanded exact machining, rare materials, and production techniques beyond Germany's reach. Even when German physicists designed microwave radar on paper, the devices remained theoretical. Germany simply lacked the means to build them. The systematic study of captured American technology, continued through 1944 as Allied forces advanced up the Italian peninsula and prepared for the invasion of France. Each new discovery only reinforced the overwhelming evidence of American technological dominance. Improved radios appeared regularly. The SCR-694, introduced in mid-1944, provided frequency modulation tank communication with increased range and reliability. The SCR-6119 aircraft radio offered hundreds of crystal-controlled channels and near-instantaneous frequency switching. Most significantly, American equipment reliability improved continuously. Early production SCR-300 radios had occasional problems with moisture ingress and battery contacts. Captured examples from late 1944 showed redesigned cases, improved seals, and modified circuits that eliminated these issues. The Americans were not just building equipment. They were continuously improving it based on field experience and incorporating lessons learned into ongoing production. German equipment, in contrast, often degraded in quality. As the war progressed, material shortages forced substitution of inferior components. Skilled workers were drafted into combat units, replaced by less experienced personnel. Quality control suffered as factories focused on quantity over reliability. Radios that should have lasted for years began failing after months of service. By the time of the Normandy invasion in June 1944, German technical intelligence had documented the complete picture of American communications superiority. Allied forces landing in France carried more radios than the entire German army possessed. Every Allied company had radio contact with battalion headquarters. Every Allied battalion could reach division command. Artillery forward observers directed fire from dozens of kilometers away with perfect accuracy because their radios never lost contact. German commanders attempting to coordinate defenses found their communications breaking down under Allied jamming, artillery fire, and the simple chaos of battle. Radios that worked perfectly on test ranges failed in combat. Crystal oscillators drifted off frequency in the Norman summer heat, making contact between units impossible. Battery-powered sets ran down quickly because replacement batteries were unavailable. The communications network that German doctrine assumed would exist simply ceased to function under combat stress. The technical reports flowing back to Berlin became increasingly desperate in tone. Oberon engineer Hermann, now attached to Wehrmacht operations staff, wrote in August 1944 that Germany had already lost the electronic war. American jamming equipment, direction-finding systems, and signal intelligence capabilities allowed the Allies to locate and target any German radio transmission within minutes. German codes were broken, frequencies were monitored, and movements were tracked through radio traffic analysis. The final collapse came in late 1944 and early 1945 as Germany's industrial base disintegrated under Allied bombing. Factories producing radio equipment were priority targets. Telefunken's Berlin facilities were destroyed in November 1944. Lorenz production plants in Stuttgart were bombed repeatedly. The Crystal production facility in Sudetenland fell to Soviet forces in January 1945. By March 1945, German radio production had essentially ceased. Existing equipment continued to function, maintained by increasingly desperate field technicians who cannibalized parts from damaged sets and improvised repairs with whatever materials they could find. Replacement radios simply did not exist. When a headquarters radio failed, commanders lost contact with their units. When tank radios broke down, armored formations became isolated groups of vehicles unable to coordinate action. The Americans, meanwhile, continued improving their equipment even as victory approached. New radios introduced in early 1945 offered enhanced range, additional channels, and improved reliability. Production continued at full capacity, not because more radios were needed, but because the industrial machine could not easily be stopped. By May 1945, American depots were filled with excess radio equipment that would never be used in combat. The end came on May 8, 1945. Germany surrendered unconditionally to Allied forces. Among the items catalogued by occupation authorities were the technical intelligence reports from Tunisia, Sicily, and Italy. These documents, classified most secret by German authorities and hidden in salt mines and underground archives, provided Allied investigators with a unique perspective on their own equipment. American technical teams searching through German facilities in the summer of 1945 were surprised to discover how thoroughly the Germans had examined captured American radios. The reports were accurate, detailed, and professionally done. They correctly identified American technical advantages and honestly assessed German inability to match American capabilities. One report written by Oberon engineer Klaus Hermann in April 1945, as Soviet forces closed on Berlin, served as his final testament to the technical war. He wrote that Germany's defeat was inevitable from the moment German engineers opened the first captured American radio in Tunisia. The frequency crystals, automatic circuits, and modular design revealed an industrial philosophy that Germany could never match. The Americans had industrialized warfare itself, applying mass production techniques to every aspect of military equipment. Hermann concluded that future wars would be won not by the side with better soldiers or superior tactics, but by the side with greater industrial capacity to produce high-technology equipment in overwhelming quantities. Germany had excellent soldiers, competent generals, and adequate tactics. What Germany lacked was an industrial base capable of matching American production. This lack was most clearly visible in something as simple as a radio crystal ground to precision tolerances by teenage girls in factories that produced millions of units annually. While German laboratories struggled to make thousands, the post-war fate of the German engineers who examined captured American equipment reflected the realities of the New World Order. Klaus Hermann was recruited by American authorities in 1946 and spent 2 years documenting German radio technology for United States intelligence. He later worked as a consultant to American electronics companies, helping them understand and improve upon German innovations that were worth salvaging. Many of his colleagues followed similar paths. The brain drain from Germany to America, formalized in Operation Paperclip and similar programs, transferred thousands of German scientists and engineers to the United States. They brought knowledge of German technology, but more importantly, they learned American industrial methods, mass production techniques, and the organizational philosophy that had made American victory inevitable. In 1952, Hermann published a technical paper in the Institute of Radio Engineers Proceedings titled Comparative Analysis of German and American Military Radio Design Philosophy, 1939. 1945. The paper based on his wartime experience examining captured American equipment, documented in academic language what he had reported to Wehrmacht High Command nearly a decade earlier. American radio design, Hugh wrote, prioritized ease of manufacture, simplicity of operation, and reliability under all conditions over technical sophistication or component efficiency. German design sought technical excellence, theoretical perfection, and component economy, assuming that skilled operators would compensate for equipment limitations. One philosophy scaled to millions of units and global deployment. The other did not. The paper became required reading in engineering schools and military me's. It influenced a generation of American engineers who designed equipment for the Cold War, the space race, and the computer revolution. The lessons learned from examining German engineers, examining American equipment, shaped American aid technological dominance for decades. By the 1980s, many surviving German engineers who had worked in technical intelligence during World War II, gathered for reunions and historical conferences. They shared memories, compared notes, and reflected on their experiences. Klaus Hermann, then in his 70s, gave presentations on his work examining captured American radios in Tunisia and Italy. At a conference in Munich in 1986, he displayed photographs of the first SCR-508 his team had examined in February 1943. The images showed young German engineers leaning over the opened radio case, measuring circuits, documenting components, and struggling to understand what they were seeing. Herman told his audience that the moment they removed the first crystal holder and saw 10 precision oscillators installed in a standard tank radio, he knew Germany had already lost the war. The frequency crystal, a small quartz wafer ground to exact dimensions, represented the intersection of physics, engineering, and industrial organization. It was not a complex device in principle. Any competent laboratory could produce one, but to produce millions to a standard quality level with perfect interchangeability at a cost low enough for installation in every military radio required an industrial infrastructure that Germany simply did not possess. That infrastructure, created in America between 1941 and 1945, did not dissolve when the war ended. It expanded and evolved, producing transistors, integrated circuits, microprocessors, and eventually the computers and communication systems that define the modern world. The same companies that had mass-reduced radio crystals for Sherman tanks later produced semiconductors for space missions, microchips for personal computers, and the components that enabled global telecommunications. The lessons learned from German engineers examining Americans' equipment in Tunisia became part of the foundation of modern technology. Design for manufacture. Standardize components. Train operators simply build test into the process. Scale production to meet demand. These principles, visible in every aspect of American radio equipment in World War II, became the standard methodology for all high-technology industries. In 1995, on the 50th anniversary of the war's end, the Smithsonian Institution opened an exhibit titled Communications and Victory: The Radio War in 1939 to 1945. Among the displays was an SCR-508 tank radio, serial number matching the unit examined by Obering Herman in Tunisia in February 1943. The radio had been recovered from German archives and returned to the United States as part of a cultural exchange program. Beside the radio, the exhibit displayed excerpts from German technical intelligence reports translated into English, documenting the examination process and findings. Visitors could read Herman's observations about crystal quality, circuit design, and manufacturing sophistication. They could see photographs of German engineers measuring components, testing circuits, and recording data. The exhibit made clear that German technical experts recognized American superiority, reported it accurately to their superiors, and understood its implications. The exhibit also displayed German radio equipment for comparison. AFUG G5 tank radio sat beside the American SCR-508, allowing direct visual comparison. The German radio was larger, heavier, more complex to operate, and less capable in every measurable way. It represented excellent engineering constrained by limited industrial capacity. The American radio represented adequate engineering multiplied by unlimited industrial resources. The curator's notes explained that the exhibit was not about praising American technology or denigrating German equipment. Both sides had competent engineers who designed effective equipment within their constraints. The difference was not intelligence, training, or theoretical knowledge. The difference was industrial philosophy and manufacturing capacity. Americans built systems that worked reliably when operated by minimally trained users. Germans built systems that worked brilliantly when operated by highly trained experts. One approach scaled to global war. The other did not. The final display in the exhibit was a small glass case containing a single radio crystal recovered from the SCR-508 examined in Tunisia. The crystal, no larger than a postage stamp, was precisely cut quartz in a hermetically sealed metal holder. The label explained that this crystal, one of 10 installed in a standard American tank radio, represented approximately 40 hours of German skilled labor to duplicate. The Americans had produced over 100 million such crystals during the war, an output that would have required every German radio technician to work for 500 years. The exhibit attracted over 200,000 visitors during its year-long run. Many were veterans who had operated the radio equipment displayed. Some were engineers interested in technology history. A few were historians studying the industrial aspects of warfare, all left with a deeper understanding of how industrial capacity determines military outcomes. Klaus Hermann died in 1997 at age 84. His obituary in the Institute of Electrical and Electronics Engineers Spectrum magazine noted his contributions to radio technology, his work in technical intelligence during World War II, and his post-war career helping American companies understand German innovations. The obituary also mentioned his lifelong insistence that Germany's defeat was determined not on battlefields, but in factories, not by soldiers but by production workers, not through tactical failures but through industrial limitations. His papers donated to the Deutsches Museum in Munich included over 2,000 pages of technical reports, circuit diagrams, component specifications, and strategic assessments written between 1943 and 1945. These documents provided historians with detailed insight into how German technical experts viewed American equipment and what they reported to Wehrmacht High Command. Perhaps the most poignant document in the collection was a personal letter Hermann wrote to his wife in April 1945 as Berlin fell to Soviet forces. He had sent his family to relatives in Bavaria months earlier and remained in Berlin performing final technical assessments until ordered to evacuate. In the letter, he wrote that he was about to destroy all classified documents and equipment to prevent capture. He reflected on the 3 years spent examining American equipment from the first SCR-508 in Tunisia to the latest radar sets captured in the Ardennes. Every example, he wrote, confirmed the same conclusion. America possessed not just better equipment, but a fundamentally different approach to warfare. They had industrialized everything from radio crystals to entire armies, applying the same mass production philosophy that built automobiles and refrigerators. Germany, Hermann wrote, had tried to fight an industrial war with craftsman methods. It was not that German technology was inferior. In many areas, German theoretical knowledge exceeded American, but theory does not win wars. Production capacity wins wars. The side that can build more tanks, more aircraft, more radios, and more everything will eventually overwhelm any opponent, no matter how skilled or brave. He concluded the letter with a prediction. The next war, if it came, would be even more industrial than the last. Victory would go to the nation with the greatest manufacturing capacity, the most advanced technology, and the ability to produce precision components in unlimited quantities. America had demonstrated these capabilities between 1941 and 1945. Any future opponent would need to match or exceed American industrial power, something Hermann believed was impossible for any single nation. History proved him correct. The Cold War that followed, World War II, became a competition of industrial capacity, technological innovation, and manufacturing capability. The Soviet Union, despite continental resources and massive population, could not match American electronics production, computer technology, or industrial automation. The gap that Hermann identified in radio crystals in 1943 expanded to encompass semiconductors, microprocessors, and integrated circuits. The story of German technicians examining captured American radio equipment is ultimately a story about industrial warfare and the revolution in manufacturing that occurred in America during World War II. It is about the transformation of warfare from an activity primarily determined by tactics, training, and courage to one determined by industrial capacity, technological sophistication, and manufacturing efficiency. The frequency crystals that so impressed Hermann and his colleagues were not magic. They were precision engineering, yes, but more importantly, they were precision engineering scaled to mass production. American industry had learned to produce millions of units to identical specifications, something that had never been done before at that scale. This capability developed for radio crystals extended to every aspect of military equipment and eventually to every consumer product America manufactured. The lessons learned by German engineers examining American equipment in Tunisia, Sicily, and Italy were harsh, but clear. Superior individual equipment means nothing if it cannot be produced in quantity. Sophisticated technology is useless if operators cannot reliably use to it. Theoretical excellence is worthless if manufacturing cannot achieve it consistently. Industrial capacity properly organized and directed defeats everything else. These lessons, purchased at the cost of Germany's defeat, became the foundation of modern manufacturing philosophy. Design for manufacture. Build in reliability. Train operators effectively. Sustain equipment properly. And scale to necessity. The concepts evident in American radio systems during World War II now underpin industrial production across every sector. Ultimately, the narrative that began with senior engineer Klaus Hermann prying open a captured radio casing in Tunisia in February 1943 ended with a complete transformation of how nations organize and wage war. The radio crystal, that small shard of precisely engineered quartz, became an emblem of the industrial revolution in military technology. It symbolized the moment when triumph ceased to depend chiefly on battlefield skill and began to hinge on manufacturing output. The German specialists who analyzed American hardware recognized this transformation as it unfolded. Their evaluations recorded not merely technical data, but the close of one era of warfare and the dawn of another. They observed, assessed, and reported the coming age of conflict. That their warnings went largely ignored in Berlin did not lessen the accuracy of their conclusions. Today, the fundamentals they identified, mass fabrication of precision parts, automated production, standardization for easy replacement, and design for efficient assembly, form the backbone of every advanced technology industry. A direct connection runs from radio crystals cut in U.S. factories in 1943 to microchips fabricated in Asian foundries in the 21st century. The industrial mindset remains identical, only the magnitude has evolved. The German analysts who tested, seized American communication gear in 1943 were not merely studying equipment. They were glimpsing the future of warfare, technology, and organized production. Their meticulous reports, once classified and archived during the conflict, eventually became historical records, explaining not only why Germany was defeated but how manufacturing strength decides the outcome of modern wars. Their final judgment, couched in technical phrasing but unmistakable in sense, was that Germany had confronted the world's greatest industrial nation with wholly inadequate productive capacity. The radio crystal, a precisely cut quartz oscillator produced by young American women in volumes Germany could never equal, told the entire story. Industrial warfare demands industrial strength. Without it, no level of tactical brilliance, inventive genius, or personal valor can secure victory. That lesson, first realized by German engineers studying captured American equipment in hidden laboratories throughout occupied Europe, still holds true today. In an era of microelectronics, satellite links, and digitally guided warfare, the essential reality remains unchanged. The side with the superior capacity to manufacture high-technology systems in vast quantities will ultimately dominate. The United States proved that between 1941 and 1945. The rest of the world has been adjusting to that truth ever since.